Okay, so this is our last lesson for the calc unit, and it doesn't mean it's the hardest lesson, okay? I'm not really sure why we waited until now. Maybe so that we had a lot of derivative tricks up our sleeve, you know, to make this smoother or something. Okay, so we're going to talk about continuity and differentiability. I want to remind you what we've thought of these in the past as. We used to call this continuity just means can draw without lifting your pen. And differentiability just means smooth. No sharp turns, you know. No sharp turns. But do you think that that's a scholarly and professional way to state what continuity and differentiability is? If your college professor says, please define continuity. All right, class, ready, go. If you wrote, I can draw without lifting my pen, do you think that sounds really professional? Not really very professional. How about define differentiability? Smooth. Okay, that's kind of maybe a vernacular way to understand it, but that's just not scholarly at all. It's not even mathematical, right? I don't think we have a symbol for smooth in mathematics, right? So we have to be a little more formal today. So let's talk first about continuity. What does it mean to not lift your pen? Okay? So I'm going to draw a picture of a graph that's continuous at 5. This is continuous. F of x is continuous at x equals 5. It looks like it might even be continuous at all real numbers. And then I'm going to draw 3 pictures where f is not continuous at 5. Okay? So f of x is not continuous at x equals 5. Here we go. 3 full pictures. First one, we have a hole at 5. Okay? And the second one, we have an asymptote at 5. And it's one of those situations where the left side goes up and the right side goes down. And the third picture, we have a jump at 5. Maybe the coordinates of this white point are 5, 3, and the coordinates of the black point there above it are 5, 6. But for one reason or another, all 3 of these pictures are not continuous at 5. You have to lift your pen to draw through 5. Okay? Now, out of all 3 of these, which one do you suppose is most likely, most often, mistaken for continuous? Which one looks the most continuous? The first one is kind of the least broken, right? You have one missing point, right? You have one missing point. You could say, this is some mathematical language you could state. You could say that the limit as you approach 5 from the left and the limit as you approach 5 from the right are the same, right? You could say that. It's true. As you come from the left and the right, you're approaching the same y value at least, which is not true for either of the other 2 pictures. Another way to say this in a little bit less writing is to say that the limit exists at 5, which, again, is not true for the other 2 pictures. So let's go and write both of those. I wrote it here in red. I'm also going to write it in green. This is kind of how you would say it. The limit exists at 5. Everything I say is important. Everything I write is important. Remember that? Okay. So some of you just sit there and stare at the walls, and you're never going to reproduce this stuff if you don't at least write it once. The limit exists at x equals 5. But that doesn't make it continuous, see? It's not continuous because even though the destinations of the curves are both approaching the same y coordinate from either side, the function itself is not defined at 5. So there is a hole, in other words, a missing point. So what's the but statement on this? But f of 5 is undefined. Right? F of 5 is undefined. Now you might say, okay, well, Mr. Shore, what about this situation? I'm going to put a green dot directly above that open hole. Is it continuous now, folks? No. Because, why? Why is it not continuous? Because f of 5 doesn't match nicely with the limit at 5. You see, there is an f of 5. It just isn't in the right spot. It's not in the hole. So the limit exists, the point exists, but they don't match, you see. So another reason why you have to lift your pen here. So if the green point is absent, you would say f of 5 is undefined. If the green point doesn't fit, you would say f of 5 doesn't fit the limit. Right? Now the other two are a little more broken. These two graphs both don't even have a limit. Right? The limit at 5 does not exist. So the limit as x goes to 5 of f of x does not exist. Why are both of these DNEs? That rhymes. Why are both of these DNEs? Why? What does it mean for a limit to not exist? From the left, from the right, we have what? Different y destination, right? So there's no way on earth you could ever draw this without lifting your pen, because as you come from the left and the right, it's different y coordinates. So how in the world could you pass through that point? You can't. You have to lift your pen. There's no two ways about it. So these are all discontinuous for some reason or another. That first one is easiest to fix, and we call it a removable discontinuity. So let's title that one. That one's just kind of special, and it's the one that deserves most of our attention today, actually. So let's pick a color here. This will be called removable. These other two are not removable. Removable what? What are we removing? The discontinuity. It's a removable discontinuity, which is kind of a double negative. If you remove a discontinuity, you've just made it continuous, you see. In other words, some graphs we can just plug the hole. Other graphs are more hopelessly broken. You cannot fix either of these two graphs by plugging a hole. You have to completely rewrite the functions to make things work. So that brings us back to our first picture at the top. What makes this graph up here continuous? What is so special about this? We don't have to say anymore we can draw without lifting a pen. We can use limit language to say the same thing. You want to say it? Well, the domain is all real numbers, but that's actually true on this graph too, our first broken one. When I plopped that green point above that open hole, I just made the domain all real numbers. Right? But that didn't fix the continuity. What is it about my graph at the top of the board that makes it continuous at 5? Why is it continuous at 5? This is so important. This is one of the most important topics in all of calculus. Why is it that you don't have to lift your pen? How do you use math language to say that? Matt?
F of x, well, wait, we can't just specifically say for 5, right? We have to say
I want to talk about 5. Right?
Oh, so just say for 5.
I want to just talk about 5.
Okay, so
Convince me it's continuous at 5
So
without
F-
saying anything about pens.
Okay, so f of 5 is equal to the limit as x approaches, the limit of f of x as x approaches 5
Okay, say that again. So you said f of 5
is equal to
the
limit of f of x as x approaches 5.
like this?
Yeah.
That's math language. What does it mean?
It means that the limit is also a point on the graph. So as both sides approach a single point, if that point is there.
Okay. What are you going to say, Jack?
I was going to say, well, not for phi, I was just going to say f of x is equal to the limit of f of x for the entire graph. So
And it's actually true on this whole graph, but I was specifically thinking about 5, and you're absolutely right. So what's going on here is, if you want to study the point 5 f of 5, which is that black dot I have there, right? This is the point 5 f of 5. There's two questions you can do here. You can find f of 5, which is kind of like just pre-calc, finding the y-coordinate, you know. Or you can study the graph nearby. That's called finding a limit, right? So what Matt is saying, I think, is if one student finds f of 5, and let's say they get 6, they are declaring that the y-coordinate here is 6 for that black dot. That's the 0.56. And another student might come along and do the calculus problem where you find the behavior of the graphs near 5, and they determine that both sides converge upon y equals 6. So now you've got the function value matching with the destination value, and that's why you don't have to lift your pen when you draw through the point 5, 6. It's because when you're coming from the left, you're approaching 6. When you're coming from the right, you're approaching 6. When you're at 5, you're at 6. And we have a perfect three-way agreement between the left limit and the right limit and the actual function value. So here is the definition of continuity at 5. Are you ready? Here it is. The definition of continuity at 5 reads like this. The limit as you approach 5 from the left is equal to the limit as you approach 5 from the right, and that in turn is f of 5. This is continuity at 5. If you ever see this statement written, or the one Matt said, which is a little bit abbreviated form of this should be pronounced f is continuous at 5. Okay? F is continuous at 5 when the left limit, the right limit, and the function all shake hands and agree on the same number. This statement in blue up at the top is so important. Okay? And obviously I'm picking x equals 5, but you can pick any x you want, right? So I just chose 5 for fun. I should have chosen 14 because 14 is my favorite number. Okay, anyway, let's do some examples here. The first one is just find the discontinuities of the function. Okay, so part A on example 1 is just f of x equals x cubed plus 5x squared minus 3x plus 6. Now in this graph, I don't think there are any breaks. I'll tell you why. It's a polynomial, right? Since it's a polynomial, its domain is all real numbers. So you can write that using our interval notation we learned in the first chapter of the year. The domain is negative infinity to infinity. There are no denominators, no square roots, no ln's. X cubed, 5x squared, 3x, and 6, they all will eat any number you give them. Right? Okay? Domain's all real numbers. There are no vertical asymptotes. How do I know? There's no denominators. Right? There are no holes. How do I know? There's no denominators. You have to have a denominator to have a hole, remember? And because of this, I would say there are no discontinuities. F has no discontinuities. Another way of saying that, F is continuous everywhere. F is continuous for all x. These two phrases mean the exact same thing. F has no discontinuities. F is continuous for all x. Okay, part B. Square root of x minus 2. this graph is a right-shifted rad graph. You should know this graph anyway. I wouldn't say its domain is all real numbers. Would you? Okay, so I think there are discontinuities. Basically, f is discontinuous for all x's less than 2. Or you could say f is continuous for all x's greater than or equal to 2. Or you could even write it this way, f is continuous on its domain. But that's not very specific, is it? So I've stated where it's broken. Where is this graph broken? Wherever it isn't. Wherever the graph doesn't exist, it's broken there, naturally. You can't say you can draw over here without lifting your pen. You can't even draw over here. Okay? You can start drawing without lifting your pen at 2. Okay? You can say that x is greater than or equal to 2 is a continuous part of the graph. Since that's just the domain of f, you could actually declare that this function is a fully continuous function. Yes, it has some broken parts, but in its domain, the parts you're supposed to draw, there's no breaks. Okay. Anyway, that one's pretty basic. Don't forget to mention the discontinuities that are just out of domain. Okay? How about this one? F of x equals x squared minus 4. I meant to do that on the bottom. I meant to put x minus 2 on top. And x minus 2, x plus 2 on the bottom. So maybe you factored it and it looks like this. Where are my discontinuities? Yeah, you could say f has a hole. F has a hole at x equals, now is that going to be at 2 or negative 2? 2. Good, because that's the one that cancels. Good. And what's going on at x equals negative 2? Yeah. The one that's not canceling, that's a VA. A vertical asymptote at x equals negative 2. So does it have discontinuities? 2 of them. A hole, and a more serious one, a vertical asymptote. Did I answer the question? Did I find the discontinuities? I did. I did even better than that. I classified them. Found and classified. What does that mean? I stated exactly what they were. I didn't just say, oh, x is not 2, x is not negative 2. I was more specific than that. Okay, yes? Jack?
If they gave you this, right?
Yeah.
They told you to find discontinuities, but they also put x is not equal to 2 and x is not equal to negative 2. Is that still discontinuous?
Okay, let me say something about, I think what you're getting at is, how do we write the f is continuous statement?
No.
No?
I'm saying, it's like, if they change the domain of the function, like they
Let's
have,
put the cell phones away, okay? You don't know this stuff yet.
like right now, they have this function, right? And then if they put, like, you know, an addition for the domain, and like, say a piecewise function, right? And at x equals negative 2, they made it a different function that was continuous with the function, rather than an asymptote or a
Okay.
hole. Would that be continuous or discontinuous? Or just said that those two places don't exist in the domain?
Okay, there's a play on words here, okay? You need to know that there's 2 phrases that we use. One is f is continuous for all x other than negative 2 and positive 2. Okay, so I'll write them for you. I need to write these so I can answer your question. Okay, f is continuous. I never wrote a sentence like this. At all x's except plus or minus 2. That's a true statement. But here's another true statement that might surprise you. F is a continuous function. how can f be a continuous function? It has breaks in it. Yes, but those happen at points out of domain. Okay? I thought so. This is a real subtlety. If I say a function is a continuous function, that does not mean it has no breaks. It means it has no breaks in its domain. This is really hard to understand. I can give you some examples, though. See, this graph, when you're sketching it, you're not allowed to draw at -2 or 2. It's forbidden. Okay? But the parts you are allowed to draw have no breaks in them. So we call it a continuous function, even if it has breaks. The parts you're supposed to draw are nice and connected, you see. Can you find a graph on this board here where you're supposed to draw for every x, but there are breaks?
Oh, wait, no, not time.
Int
X.
Int x is very unique. What's the domain of int x? All real numbers. You can draw a vertical line anywhere you want. It will contact the graph. But there are jumps all over the place. This is a graph. This is a discontinuous function. All the rest of these are continuous. You say, are you kidding me? Tan? That thing's got an infinite number of asymptotes. Yeah, but you're not supposed to be drawing at those points. Tan is a continuous function because for the parts you are supposed to graph, those are all connected. The int function is not a continuous function because the parts you're supposed to draw are broken. You even draw at x equals 1, but it's broken. I'll talk more about that next year, the difference between a continuous function and a function that's continuous. Not the same meaning at all. All right? That's a little confusing. This just means continuous on its domain. That's very subtle, and it won't be on my test, but it answers Jack's question, I think.
Yeah.
Okay, good. Okay, so for my second example, we're going to try to force a line and a parabola to form a continuous situation. So here's a parabola, and here's a line. And so at x equals 4, we know that these two are being kind of coming together. We're trying to make kind of a glued together line slash parabola situation. And I don't think I really want to draw this, but if we want this to be continuous at 4, then we basically need for the limit as x approaches 4 from the left of f of x to match the limit as x approaches 4 from the right of f of x. And this should in turn match f of 4. Okay? All right, so this will prove, if we set this up, we're forcing the limit to exist. That's this first part. And we're forcing that same limit to equal f of 4. Okay, so this, basically, if we use the left piece, that's the green one there. We don't need the superscript anymore. So we'll plug in the 2ax minus x squared here. And then coming from the other side, we'll use the 2 minus 3ax. Okay, so what I did here is, since I already chose the pieces, this is the parabolic piece that represents the left side, and this is the linear piece which represents the right side. I don't need the minus and plus superscripts on the 4 anymore. Notice I dropped that. I don't need that anymore because, well, I've already chosen the left and right pieces. So why write minus and plus? It's sort of redundant, isn't it? Okay, and then this in turn is supposed to be filled by the whole. So we want f of 4 to match these. Well, f of 4 is actually known. F of 4 is, well, it's not known entirely, but we would be using this expression here, see? Because this is the expression out of the two. The linear one is the one that will accept the 4 as an input. So we'll go ahead and use f of 4 here, but what it means is we're going to be plugging in 4 into this. So 2 minus 3a times 4, see? Okay. Now evaluating our limits. So there's two of them. The first one can be found just by plugging in 4. So you just get 8a minus 16. And the second one also can be found by just plugging in 4. And you get 2 minus 12x. Now remember that, or sorry, 2 minus 12a. Remember that you actually may have to use conjugates or factoring, reducing, that sort of thing sometimes on those. But those two are pretty straightforward. And you'll notice that this is a little bit redundant also. This is 8a minus 16 equals 2 minus 12a equals 2 minus 12a. So it's normal to have a couple things that are equal here. That should have actually happened, so that's good. If you bring all the a's to one side, we get 20a. Oops, I'm not sure why it's writing in highlighter, sorry. We get 20a equals 18. A is basically 9/10. Okay, hang on to that. What does it mean? Well, the function was given, but a was missing, remember? The function looked like this. It was basically 2a x minus x squared, and this is for x's that were less than 4. Right? And then the other part of it was linear. It was 2 minus 3ax, and that was for x is greater than or equal to 4. You just found the a that actually makes this problem work. So basically you have this 2 times 9/10 x minus x squared, and 2 minus 3 times 9/10 x, and this is for x is less than 4, and this is for x is greater than or equal to 4. See? Okay, so this function is officially, they didn't really ask us to write this, but 9/5 x minus x squared is the quadratic part, and 2 minus 27/10 x, that's your linear part. Now it's kind of fun to graph these and see if they actually do match, okay? If they don't, we'll go back and look for our mistake. So we have 9/5 x minus x squared. Let's see here, where's my plotter? There it is. Let me delete these. Okay, so putting in new functions, we have 9/5 x minus x squared. There's that parabola. And then 2 minus 27/10 x. 2 minus 27/10. Oops. I put times 1, I meant to put times x. Okay, now this is for x is less than 4, and this is for x is greater than or equal to 4. So let's go back in here. Let's make sure this only goes from like negative 12 to 4. We'll lock that interval. And then when you graph it, it'll just be part of the graph. I think I did that wrong. I meant to go negative 10 to 4. So that looks like that. And then 2 minus 27x, that's for x is greater than or equal to 4. So let's get in here and do x is greater than or equal to 4. We'll just do that by going 4 to 20. Alright, now I gotta just kind of scroll down so you can see it. See that nice tight fit right there? Look at that. The blue and the black come together perfectly there. Now you'll notice there's a kink in the graph, but this is continuity. This is definitely continuity. If you want to see the actual bubbles, I'll make this a circle of size 2, and it was an open one. So there's an open circle for the blue, and then we'll make a closed circle for the black, and you'll see it's actually the black dot fills the blue open circle. We'll make the open circle a little bigger so you can see it. Okay, so a little hard to see there, but you get the point. Get it? Haha, the point. So it's a nice match there, and not very smooth though. But that's okay. They didn't ask us to make it differentiable, right? Now let's do an example where we can make this both smooth and connected. So we'd like a differentiable version of this. Okay? So for my next example, oh, by the way, the answer to this problem is simply a equals 9/10. So my next problem I chose was this one. Now this one's a little more detailed. It has an A and a B in it. Take a moment and write it down. Let's go ahead and give it a try. We're going to try to make A and B both, so that this graph is both continuous and differentiable. So this time we're at x equals 1, where we might experience a break in the graph, right? So we don't want that. We want to enforce continuity. So we want the limit as x approaches 1 from the left of f of x to equal the limit as x approaches 1 from the right of f of x, which in turn we want to equal to f of 1. So if we just choose the left piece, we can drop the superscript. notice it's the b plus 3bx that's actually the left piece here. You should convince yourself of that. And this right-hand piece is x squared plus ax. I don't need the superscript if I put in the right-hand piece. And lastly, f of 1. f of 1, you're going to have to use this expression here, basically 1 squared plus a times 1. So 1 squared plus a times 1. In other words, this then becomes b plus 3b equals 1 plus a equals 1 plus a. There's your redundancy. And last time we got to this point, we were done. But you'll notice we got an equation with a and b. What's going on? Why is this happening? Well, what's happening is to provide connectedness, we just have to ensure that 4b is 1 plus a. But that leaves open a whole infinite number of possibilities. In other words, there's an infinite number of ways to connect these graphs, either by choosing a b that works here and then calculating a that works, or by choosing an a that works and calculating the b that works. So that's not the end of the story. We're trying to make this thing smooth. So that being said, we would then need to set up a differentiability argument. So now we're going to try to make sure that the slopes match perfectly. Okay, so without getting too theoretical here, we're just going to kind of repeat the same thing. But this time we want the limit as x approaches 1 from the left of f of x, or excuse me, f prime of x, to equal the limit as x approaches 1 of f prime of x. See? And if we want to, we can also go on and put the f prime of 1 here. I think it's more optional there. But let's just go ahead now and put in the derivatives, and we'll force the same idea here onto this. So f prime is, remember a is a number, so when you take the derivative of x squared, you get 2x. When you take the derivative of ax, it's just a. Just like the derivative of 5x is 5. The derivative of ax is a. So we get 2x plus a for this derivative. So this is just 2x plus a. And then this one, oh, I forgot to put the plus up here. And I don't need to put the minus on the second line. So I basically just made two changes. I put the plus there because I forgot to write it earlier. And here I don't need the superscript, remember, because I'm plugging in the pieces, the derivatives of the pieces. So let's go back up and see what the derivative of the right piece is. So the derivative, I reversed this. I'm sorry, guys. The right piece is the 2x, hold on. The right piece is the x squared plus ax. So the 2x plus a is supposed to go here. Sorry. This one is the left piece. So I got a little distracted there. I had a student come in. So I'm okay now. B plus 3bx. What's the derivative of b plus 3bx? Well, b is a number, so the derivative of that's 0. 3bx is like having, 30x. So 3b is the coefficient on the x. So if you bring the 1 down, you get 3bx to the 0. So basically the slope of this b plus 3bx is simply 3b. So this is just simply 3b. And then as for this f prime of 1, we just have to pick the function that will allow us to plug in 1. That's actually the first one, x squared plus ax. So the derivative of that was 2x plus a. We're plugging in x equals 1. Okay, so this becomes, since there's nowhere to plug in the x, just simply 3b. And here, there is a place to plug in the x, so let's plug it in right there. So we get 2 plus a. And this is also 2 plus a. There's that redundancy. And we learned that 3b is 2 plus a. This comes from forcing differentiability, forcing a smooth situation. So now we have two equations. You can see them. I'll highlight them again. So we basically have this in yellow up here and this in yellow down here. And it's time to solve. So 4b equals 1 plus a. 4b equals 1 plus a, combined with 3b equals 2 plus a. Solve this however you like. You have many methods, But let's go ahead and subtract these maybe. And we learned that b is negative 1. Which means that 4 times negative 1 equals 1 plus a can be solved. And a is evidently negative 5. A is negative 5. Oops, there it goes again. All right, so what did we accomplish here? This is really cool. A is negative 5 and B is negative 1. So let's rewrite our functions. F of x was x squared plus ax. That looks like this. And remember, this is just for x is greater than 1. And then that's if you plug in a equals negative 5. We also have this b equals negative 1, which means that this is going to be negative 1 minus 3x. This is the fun part. Let's go graph it and see how well we did making a smooth and connected situation. So x squared minus 5x is our first function. X squared minus 5x. And negative 1 minus 3x. Negative 1 minus 3x. Alright, this is cool. Check this out. We have the black and the blue fitting this time. Only, this time not only do they fit together, but it is perfectly smooth. Look at that. Once you zoom in really, really close, and we are extremely close right now, at the point 1, negative 4, we have a connected graph and a smooth graph. If you're really zoomed in, it looks like a straight line, of course. That last graph wouldn't look like that because there was a true corner there. As you zoom back out, you kind of see this as what maybe an engineer would have to do if they're designing a roller coaster. So if an engineer wanted to design a roller coaster, they would want the place where the curved tracks and the straight tracks meet to not only be connected properly, but to also have a perfect continuity of slope there. Otherwise, you're going to feel a slight jaggedness in the train going through there. So you're going to feel a jolt, like some rides, at amusement parks sometimes give you a headache. It's probably because the tracks are maybe connected properly, but not the slopes. The slopes are not good, not continuous through there. So we provide a continuity of y-coordinate and continuity of slope, providing a nice smooth transition there. What happens if you just change the slope just a little tiny bit? This is something you would feel on a roller coaster. Actually, if you look real closely, I just changed the 3 to a 2.9. We just got a gap right there. And even if you try to downshift to fix it, the slopes aren't right. So it's just not right anymore. It was when this was a perfect 3 that we have this perfect setup. All right, so that's my lesson for continuity differential and differentiability.